Okay, so we're gonna talk about general differential equations. How general differential equations look like. So the first way to classify differential equations are the following. So you could consider this equation. Um, so this is a first order differential equation because it has one derivative. Remember, I talked about that in the previous video, right? And then this is another, this is first order, this is second order differential equation. Why? Because it has two derivatives. And so on. You have three derivatives, then you will have third order. But so when you have first order, you just need one extra condition. Let's say y of 0 equals 0, right? And here you will have more conditions. Or you could have that one, or you could have y prime of 0 equals 0. So either way is enough for the first order. For second order, you need two conditions. You need you could say y of 0 equals 0, y of 1 equals 0, or 10, let's say. Or you could say y prime of 0 equals 5, y of 0 equals 7. Okay, so those are possibilities for your initial conditions. So what about more orders? Well, you increase the order, you will have a third order, fourth order, and so on. So in general, how a differential equation look like? In general, how a linear differential equation looks like. So a linear equation, we can write it like this: a n x n derivative plus a n minus 1 x n minus 1 derivative of the y, right? And so on until a1x dy dx. Let me make it smaller here. Plus a0x y equals g of x. So all these guys, this general equation is linear. Okay, so you might have this high order. So you have. Sorry, this is my Siri giving me problems. You might have. You might have different orders of derivatives, but that means it's a higher order differential equation. Okay, but it's linear. So right now, first we're gonna deal with linear differential equations. Okay, well, actually we're not gonna do nonlinear. We can do a few nonlinear. We might do one nonlinear, but in general we're gonna do linear. Okay, so to do nonlinear, you could do a master thesis in a nonlinear equation. You can get a nonlinear equation, study the model, and then do some numerical simulations, because usually it's very hard to solve. And if you can solve, then you can have a little paper probably. Okay, there are different methods to do that. Several faculty here at UTRGV do nonlinear differential equations. I do those nonlinear differential equations. Okay, so this is higher order. So since I have n derivatives, how many conditions I'm gonna need? I'm gonna need n conditions. So you could say y of x0 equals y of 0, then y prime of x0 equals y1, and then y of n minus 1 x0 y n minus 1, right? So these are n because I started on 0. So that could be a possibility. Okay, and remember, I'm using this notation. Means y n minus 1 means derivative, no, sorry, n derivative, n minus 1 derivative with respect to y. Okay, so this is as notation to say n minus 1 derivative. Okay, so but really what are we gonna do? We're gonna start with second order and we're gonna do first order. We can do more. I'm gonna teach you a method that is called Laplace method. You had to see it when you were in undergraduate. We will review that. Um, and the good news of Laplace is that you can deal any linear higher order the differential equation with the same method. So, but then the good news is we can use the computer algebra system, for example, to help us to solve it. So, in general, we focus first on a second order differential equations. Okay, so this is a second order differential equation. Okay, and then you can have, for example, you need two initial conditions. So need conditions. I apologize for my writing. I'm not very comfortable writing on this computer. My arm is kind of in the air, so y of x0 equals y of 0, or y prime x0 equals y1, or the possibility could be y of a equals y0, y of b equals y1. Okay, so those are possibilities. So we'll solve this equation with these conditions or with these conditions, for example. Okay, so that's what we're gonna do. And guess what? Quadratic formula is gonna be fundamental to help us. For these first methods, we are gonna do. Later, we just gonna do Laplace transform, and then we don't need to do second order. No, we don't need to do quadratic formula, but I thought it would be a good idea to do this with quadratic formula, so you motivate your students, and maybe you can prepare a representation of applications of quadratic formula or interesting applications of quadratic formula to your students. I don't know. So there is a property here. So there is let's call it a theorem. This theorem is called the superposition principle. So I'm gonna upload a free book. And I'm gonna load a free book in the materials, the course materials. So, and also you can download it. You can just do click and download it. But you will find a complete definition of this. You know, we have to be careful. So when we define things, but I want to go. This is more like a discussing the general concept. Okay, so I don't want to be too rigorous right now. But let's say you have two solutions. Suppose y1 of x and y2 of x are solutions of a star. So this, let's call this star, the second order differential equation. But well, no, let's not call this one star. Of the homogeneous one, because this one is not homogeneous. I don't want to have to raise this. So of the homogeneous version of a star. Well, guys, call it star. So what is the homogeneous version of a star? Means g of x equals to 0. So my equation is a of 2 of x second derivative plus a1 of x dy dx plus a0 of x y equals to 0. So you have two solutions for this guy. Is homogeneous, is linear. Then by the superposition principle, then y of x equals a constant times the first solution plus another constant times the second solution is also a solution. Okay, so this is interesting because that's the secret of sound waves propagation. So you are blowing or playing a flute, right? So that is one wave, and then you are playing the piano. This is another wave. So these waves interact somehow, right? So you can add them, and then you'll have another wave, right? So that's kind of that's how waves interact. But here is more interesting. Here is more, for example, one model for a second order differential equation. So imagine you have a spring and you have a mass, and then this start oscillating, right? So this is going up and down, going up and down. So two solutions. So you have one solution for this equation. So this equation can model something like that if these guys are constant, and if they are oscillating, right? So if you have one solution for this model plus another solution, the sun will be also a solution. Okay, so if you have two waves, two electromagnetic waves, right? So two electromagnetic waves, right? They can interact with the two of them. Okay, remember in my slides I talk about Maxwell equations. Okay, in particular, if you want to make it easier, from Maxwell equations you can derive this equation that is called the wave equation. This is a constant. So, but this is a partial differential equation. We'll do this later in the class, so it's okay for me to talk about this. So this is a wave equation. What is a wave equation? So this is a function of two variables. So okay, let me be more precise since it's the first time that I write it down. So you get UTT, or UTT means second derivative with respect to time of U, okay? Equals C UXX x of t. So this, in other words, this means, and then we use this weird notation D. Second derivative of U with respect to time, xt, and then constant, excuse me, second derivative of U with respect to x and t. Okay, so that was the part of the slides that I didn't want to talk about. Is eventually I have to talk about. So in the slides you can find it. So this is the wave equation. No, so this is notation or this is notation is okay. So that means that models, for example, if you have a guitar. So you have a spring and you pull it, right? So you start playing your guitar. So then she started making oscillations. Okay, so that's one wave, right? And then you make another one. So you put your finger here, and then you have another oscillation. That's a second mode. So and that start vibrating. So start doing vibration like this, right? Pan and pan. So you have two different vibrations, but they are solutions of the same equation, of the same wave equation. So they don't destroy each other. They just interact, even though they have different initial value conditions. Okay, they will have initial value conditions different, but they will still be solutions of the same equation. Okay, so that's very interesting because we are describing music here, and you can find a lot of really cool stuff. You look for Fourier analysis. We will do some of that. Okay, you can show your students really cool videos about Fourier analysis. How they hear a song and we'll split the song in the different harmonics. Okay, if you know to play an instrument, you might know something about this. Okay, okay. So this is the superposition principle, very important for linear equations. That's what makes linear equations easier or easy, basically. But you know, even though they are easy, engineers, that's the way they live. Okay, engineers use wave equation, heat equation, and they are linear, and we're gonna solve them. And most of the models they do are linear. Okay, so we will see later, and you'll see that in my video, that sometimes you have one solution. So if you have one solution, how can I construct or how can I make a second solution? And my video is not gonna show you only one solution, but one linearly independent solution. Okay, so you see my review of linear algebra. I talk about their linearly independent. So and everybody doing a master, the master you are doing, has to take linear algebra. I understand. So you might know already what is the, and I talk about the video. So what are two independent vectors, right? So let's say we have 1 and 2 and 3 and 4. How can I decide that these two vectors are linearly independent? So they are linearly independent if they are not in the same line. And how do I test that? So I make the determinant. So 1 times 4 is 4, minus 3 times 2 is 6. So I get minus 2. They are linearly independent if the determinant is different of 0. So now, if I have functions, what do I do? And probably you didn't do this in your linear algebra. Probably they do it. It's important, so probably they do it. So theorem, and did we finish our video? This video. Two functions, f1 of x and f2 of x are linearly independent if you take the function f1 of x, f1 of x, no derivative, f1 of x, and you take the other function f2 of x. Then you take the derivatives. And then you find the determinant. So this is f1 of x times f2 prime of x minus f2 of x times f1 prime of x. If this is different of 0, on an interval, for x on an interval AB, let's say, then the function are linearly independent. So this is called the Roskian of f1 and f2. So if the Roskian between f1 and f2 is not 0, so the functions are linearly independent. Okay, and you learn that two functions. So actually, the definition of linearly independency from linear algebra. So is that this is the theorem, but if you want to do the definition, so f1 and f2 are linearly dependent if there exists C1 and C2 such that C1 times F1 of X plus C2 F2 of X gives you 0. So that's the definition of linearly independent. I don't know how I'm gonna do to improve my writing. Because not probably my table is too high or something. So they are now. I know all of you guys have really good writing. Teachers have beautiful writing. I don't. Okay, so this is what it means linearly independent. Okay, and if you apply the definition to vectors, that will apply to vectors. Okay, so two vectors are linearly dependent if they are in the same line. So if you apply this definition, for example, what is linearly dependent? So example, so you have 1 1 and minus 1 minus 1. So 1 1 and minus 1 minus 1. So well, this is a silly example. Let's put minus 2 minus 2 minus 2. So I have f1 1 1. I need to find a constant that two constants such that the sum of these two guys gives me 0. So if I choose C1 equals 2 and C2 equals 1, that will give me 0. So they are linearly dependent. Okay, so same thing for here. But then this becomes really hard. Okay, so that's why it's better just to use the terminal. Excuse me. So so let's make an example and then we can go. Well, I can go, you go to the next video. So example, decide if these two functions, e to the 3x and y2 of x equals e to the minus 3x, are linearly independent or dependent. So we're gonna do, we need to do the Roscan of e to the 3x with e to the minus 3x. So we put the two functions e to the 3x and e to the minus 3x. And now find the derivative of each. So okay, so how do you see this video? So let me comment on this. So if I will recommend that you try to do this by yourself. So stop the video and do it yourself. So and also take your pencil and a notebook and start writing all that I write. Okay, if you just see the video, it's like looking a movie. It's like watching a movie. So you cannot. I don't think you're gonna understand very good. You need to interact. You need to take your notebook and start writing and stop the video. And I want to do it by myself. So you should stop the video right now and keep going. And then compare with my video. And you'll see that it's even faster for you. So I'm gonna find the derivative. So you probably come back, right? So I'm gonna find the derivative of the first one. So it's 3 times e to the 3x. And then times the derivative of the next one, minus 3 times e to the minus 3x. And now I'm gonna find the determinant. So I get minus 3 times e to the 3x times e to the minus 3x minus 3 to the 3x, right? Minus 3 times e to the 3x times e to the minus 3x. So when I get this, I will get minus 6. That's different of 0. Therefore, e to the 3x and e to the minus 3x are linearly independent. Why is this important? Because once you have one solution, you can find a second solution linearly independent. There is a formula for that, and that's the next video. Okay guys, so I'm gonna stop here. So this video has 25 minutes, so it's probably okay. What I don't like of these long videos is that I cannot upload those to YouTube, but okay, you will find a way. So let's go to the next video.